Hi, so today very quickly we're going to go through how to spec a motor for a two-wheeled differential drive robot. So remember, a differential drive robot is the one that has a wheel, left wheel, here would be the robot body, and here would be the right wheel. And so the wheels are connected through a common axis in the robot, and the robot moves in that direction. So the way you do that is you need to first come up with your desired robot parameters. So what you need to choose is a mass. I would say 1 kg. You need to choose a desired speed. So say 0.5 meters per second. And you also have to come up with the time for it to reach top speed. So I usually use, say it would take 100 milliseconds to do. And again, the last thing you have to do is choose a rotational speed. So I think a good value, 1 rotation per second. Rotation is RPS. So the first thing we're going to do is calculate roughly what our stall torque is, so torque stall, called TS. So this is done pretty easily. For now, recall that torque is equal to mass times acceleration times your lever arm, or in this case, the radius of our wheel. So that would be R. And acceleration can be found from our speed and tau values. So it would be speed divided by tau, which would be A is equal to 0.5 over 0.1, which is equal to 5 meters per second. And if you plug those in, so mass is 1 times 5 meters per second times radius of our wheel. So we can choose one based on something you can buy. At Pololu, you can get a 70 millimeter diameter wheel, so that's 35 millimeter radius, 0.035 meters. So that gives you a torque of approximately 1.75 Newton meters. Now you're going to say, well, yeah, but we also have to account for the friction of the torque of the system. Well, I mean, we could give it a fudge factor of 2, so you'd need a total of 0.35 Newton meters. But also recall that you have 2 wheels, so 0.175 seems to be about good enough. So the no-load speed can be found just by looking at the profile of a wheel. Right. So as a wheel spins, the travel distance of the robot, which it's attached to, will be proportional to the circumference of the wheel, which is 2 pi r, where this is r, right? R. Then all you have to do is come up with a desired spinning value, or the rotation speed for your motor. So we'll designate that omega, and that will give you your linear travel velocity. Now, if you recall, a DC motor has sort of a linear relationship between its torque and speed. So say this was torque and this was speed. Its stall torque is going to be somewhere around this point here, and it's going to have a linear relationship to the no-load speed, which is around here. So we can assume for a fudge factor that the robot will be operating about middle of the road, half of its no-load speed, which would be about here. So we're going to have to add, we're going to have to augment this a bit. So then to get our desired speed or velocity, we'll just assume that we're running at half of no-load speed. So 1 over 2 no load. So rearranging the equation a little bit, we end up getting something like omega no load is equal to our linear travel velocity divided by pi times the radius of our wheel. So for our robot, that means that if we want to get the no load speed, it's 0.5 meters per second over pi times the radius of the wheel, which is 0.035. That gives us 4.55 radians per second, which converts roughly into an RPM value of about 44 RPM. And so finally, to get the rotation speed of our robot, we just have to remember the geometry of our robot. So, like I said, left wheel, and then robot body, and then right wheel. And so, the robot probably contacts the ground here and here through this axis here. So to get rotation speed, it's pretty simple. Say the robot was spinning on its axis here. Its wheels would have to travel something like this for the robot to spin around. So the right wheel would be spinning forward, the left wheel would be spinning backwards, and it would rotate around like this. So this here can be described by the robot's axle length, right? Which we'll denote D. This would be axle length. And to get the rotation speed, of course, then we just have to find the circumference of the circle, which is circumscribed by this spinning behavior, which is pi d. And of course, it's this describes the distance, so distance per rotation. And of course, we know the linear travel distance of each wheel, right? Described by v, which gives us the distance per second. And so the rotation speed is very simply 1 over pi d, which is rotation per distance, times v, which is distance per second, which gives you rotations per second. So for our robot, choosing a axle length of, say, 12 centimeters gives us a rotation per second value of 0.5 over pi times 0.12, which is about 1.3 rotations per second, which is exceeds what our performance values were. So now just a bit of a recap. Remember that you want to do torque first. So that is specifies your stall torque to be mass times acceleration times the radius of your wheel. 2, you want to get your no load speed, which is omega no load. And that is given by velocity over pi times the radius of your wheel. So remember, this is in radians per second, which you got to convert. And then 3, of course, the rotational speed of your robot, and that is given by r is equal to the velocity, the linear velocity of your robot times pi, or divided by pi, times the axle length, given d here, between your two wheels, and that's in rotations per second. Thank you very much for listening to this video. Hope it helped you design some awesome robots.